Welcome to Geology 1. My name is Renee Clary, and I'm an assistant professor here in the Department of Geosciences at Mississippi State University. Geology 1, Processes and Products, is the first geology course in the Teachers in Geosciences program. This video lecture series is meant as an overview only. You will also be assigned textbook readings, instructor messages, and possibly outside internet sources and outside papers to access. As an aside, a colleague once told me that 20% of everything he lectured in front of a class was wrong. It was inaccurate. And this isn't to say that he did a bad job, but we often misspeak, and the body of science is constantly changing. As new data comes available, we are able to modify the science, and accordingly, the things that we speak and that are recorded for posterity aren't necessarily what's current in the science. So if something seems out of order, or if you need clarification or further information, please feel free to ask your online instructor or post questions on your discussion board. Let's get started. Geology 1, Processes and Products, is an overview of the science of geology, the physical science of geology. Geology, first off, is the study of the earth. How can we think of the earth? Well, we know, first off, it's very complicated. It's not a simple object at all. The earth is dynamic. It has changed quite a bit over its 4.6 billion year history. We can think of the earth as a system. A system is a combination of parts or components that work together or interact. You can see from this satellite photograph that the Earth is not simple at all. To help us understand this system of the Earth, sometimes it's convenient to think of the Earth as a mega system of interacting systems or spheres. And here we go. Here are some of the systems or spheres of the Earth. We can study the biosphere, which is a system of the living organisms on our planet. Those are the organisms in both a marine environment and a terrestrial environment. The hydrosphere is familiar to us as the water cycle. The atmosphere, the envelope of gases surrounding the Earth, is also a system of the Earth. Lithosphere may be a new term for you. The lithosphere is the crust and the upper mantle. The lithosphere is broken into plates, and this is the foundation for plate tectonics. We also have the Earth's interior. You may also hear the term regolith. Regolith is the unconsolidated debris at the Earth's surface. Now, all of these spheres interact. We're not looking at something acting in isolation at all. This is a very complicated system. We also have a technosphere. A technosphere is the interaction of the natural world with humans. Our technology has changed the Earth, and the Earth influences how we live. Here is a diagrammatic representation of the different subsystems or the spheres of the Earth. If you look at the top, you can see the atmosphere. Over to the right, the biosphere. To the left of that, the hydrosphere. And then we see at the bottom of our little diagram the lithosphere, the plates, and we can break that further down into the divisions of the planet itself. Now, although this is shown as a circle, you need to keep in mind that the spheres interact not necessarily in a nice circular motion or clockwise or counterclockwise. For example, if we look at the biosphere, this involves all the living objects, organisms of the Earth. We know that the biosphere affects the atmosphere. If we look at plants, we know that plants take in carbon dioxide and make sugar during photosynthesis, and they give off oxygen, so that affects the composition of the atmosphere. We know that the biosphere can affect the hydrosphere. Think about cities and how cities located near river systems tend to give a little bit of pollution, trash, runoff into the stream. So the biosphere affects the hydrosphere. Of course, the lithosphere is involved. The lithosphere determines how animals live, the biosphere. The lithosphere can also be weathered by the atmosphere and the hydrosphere. So the point to keep in mind here is that all of these different spheres interact, or work together. Put humans in that picture, and naturally things can get pretty darn complicated. Geology is not a singular science, just as in medicine that there are many specialties of medicine where we can have pediatrics and orthopedics. We also have different specialties of geology. Right now you're watching the video lectures for Geology 1, Processes and Products. This is a physical geology course. We study earth materials, minerals, rocks, and processes in physical geology. Historical geology, or earth history, is the teacher in Geosciences Geology 2 course. In historical geology, we look at the origin and evolution of our planet, all 4.6 billion year history of the planet. Petrology is the study of rocks. We have a special TIG course, an elective, plus 30, which is rocks and minerals. Paleontology is the study of fossils. That's my specialty. Actually, I take it down a little further. I am a micropaleontologist, and I specialize in benthonic foraminifera, which are these planktonic little foram protists. And even further than that, I specialize in Arctic Ocean forams. Now, one way to look at physical geology and historical geology is this. In physical geology, in Geology 1, we will learn the definitions and the rules of grammar, as you will. And then in Geology 2, Earth History, we will use the knowledge in Geology 1 to read the Book of the Earth. The Book of the Earth is very old, and we can think of it as being placed face down in a campfire. So the oldest chapters are charred, destroyed, or metamorphosed, and harder to decipher. We'll learn more about the history of the Earth in Geology 2. Here's a diagram showing the different specialty areas in geology as well as the related sciences. Geology is an interdisciplinary science. We claim paleontology, for example, but paleontology is also claimed by biology. Geochemistry and environmental science are also claimed in chemistry. Geophysics and the study of Earth's interior is also claimed by the discipline of physics. How does geology affect you, and why are you here? Why do we need to study geology? Geology affects all of us in numerous ways. We all live on this planet, and we don't get any care packages from Mars delivered periodically. So everything that we need must be right here. Art, music, and literature have been influenced by geology. Think of a special painting, or Aaron Copland's Appalachian Springs, influenced by the geology of the Appalachian Mountains. History and politics, geological boundaries determine different states. The Mississippi River has been a great demarcation for different states. Geological hazards, we hear a lot about this in the news. Earthquakes, volcanoes, tsunamis. Geology affects us, sometimes in not so positive ways. Resources, minerals, oil and gas, sand and gravel, gemstones. It's often said that your house comes out of a mine. And if I look around the TV studio, I can immediately see sheetrock made of gypsum, concrete made of limestone. If you look around your room, you can see things similar. In other words, if we don't grow it, we mine it. So, rocks should be our friends. Here are some old newspapers showing geological hazards that have influenced, unfortunately in negative ways, people living in the shadow of volcanoes, people living in active fault zones. Geology affects us all. We need to keep in mind the idea of sustainable development as we leave this course and live with Earth. Sustainable development is using the earth to fulfill needs without harming the environment for ourselves or for future generations. If you listen to the news, it's pretty hard to miss discussions on greenhouse effects, global warming potentials, climate change. The better you know the earth, the better prepared you are to decipher what's going on in the news and make positive choices for sustainable development. Let's start at the beginning. We're going to very briefly overview the formation of the universe and our planet. To put this in perspective, first off, I want you to think of the number of stars that we have in our solar system. You should have thought one. That's the Sun. How many planets are there, with or without Pluto? Okay, so we have one star and we have 8 planets, or 9 for you Pluto holdouts. How many stars in our galaxy? What is our galaxy? Our galaxy is the Milky Way, and according to Neil Tyson, who is the curator of the Hayden Planetarium in New York, he says that there are 1,000,000 billion stars in the Milky Way galaxy. But we're not done yet. How many galaxies are there in the universe? Again, according to Dr. Tyson, there are 1,000,000 billion galaxies in the universe. So, we are on the Earth, which is one of 8 or 9 planets, depending on whether you're a Pluto holdout or not. We are revolving around one star, which is one of 1,000,000 billion stars in the Milky Way galaxy, and that's one of 1,000,000 billion galaxies in the universe. Feel small yet? How did the universe get its start? Well, current theory is that the Big Bang occurred approximately 13.7 billion years ago. We're not sure what happened, if something banged, if something exploded, if something imploded. But we do know that 13.7 billion years ago, time and space were set at 0 in an infinitely small space. How do we know this? Well, there are different lines of evidence, including background radiation, which can still be measured, and the expansion of the universe. The universe is constantly expanding. After the Big Bang, very shortly after the Big Bang, the 4 basic forces separated. These are gravity, electromagnetic force, strong nuclear force. This is what holds the protons and neutrons together in the nucleus, and weak nuclear force. Weak nuclear force is responsible for radioactive decay of certain elements. Now, that was the origin of the universe, and that was 13.7 billion years ago. What about the Earth? Well, the current theory for the origin of the Earth is the solar nebula theory. The solar nebula theory involves the condensation and collapse of a spiral arm of the Milky Way galaxy. As this arm collapsed, rotation started. We had a mass accumulate in the center, which became our proto-sun and eventually our sun. The rest of the leftover matter was accreted or collided and stuck together into planetesimals. And as these planetesimals collided and accreted, they eventually formed planets. We have both terrestrial planets in our solar system and Jovian planets. The terrestrial planets are Mercury, Venus, Earth, and Mars, and the Jovian planets are Jupiter, Saturn, Uranus, Neptune. The terrestrial planets tend to be small and rocky with a metal core, and the Jovian planets are large and gaseous. This occurred 4.6 billion years ago, the same age as our Earth. In the beginning, our Earth was homogeneous, but differentiation occurred later and was one of the most important events in Earth's history. This diagram shows a pictorial representation of what we think happened in the solar nebula theory. It's very, very simplistic. If you start in the middle left side, you see a cloud, basically condensation of that spiral arm of the Milky Way, move counterclockwise toward the bottom, and you see circulation starting, an accumulation of mass in the center that became our proto-sun, located there in C. And slowly the rest of the matter and mass began to collide and accrete into planetesimals, and now in the upper almost left side of that diagram you see a modern pictorial view of our solar system. Pluto is still included. You note that Pluto's orbit is not in the same plane as the rest of the planets. So early Earth, at the beginning, at the birth of Earth, it was cool, wasn't hot, and it was homogeneous. The heat was caused by differentiation. The heat caused differentiation. Heat was caused by gravitational compression, radioactive decay. We have radioactive elements which are inherently unstable, and they slowly decay to a more stable daughter product, and in the process give off heat. And meteorite impacts. Meteorite impacts contributed heat to early Earth. There were many more meteorite impacts then than there are now. The differentiation is perhaps the most significant event in Earth history. Because we have a differentiated Earth, we have plate tectonics, tectonic movement, we have continents. The outgassing from Earth's interior has resulted in our oceans and our atmosphere, very different in early Earth than today. Take a look at this diagram. The far left shows you a homogeneous early Earth, and then heat from gravitational compression, radioactive decay, meteorite bombardment caused the heavier elements to melt and sink toward the middle of the planet, to the core. And now you see we have a differentiated planet consisting of a core, both solid inner core and liquid outer core, a mantle, and a crust. Okay, let's divide up the Earth based on compositional differences, which is the traditional way that we think of dividing up the Earth. We can also divide up the Earth on physical differences as well, and we'll get to that in just a second. If we look at the chemical divisions of the Earth based on compositional differences, we have the traditional core, mantle, and crust. The core can be divided into two regions: a small solid inner core made of iron and nickel, and a larger outer liquid portion. And we hypothesize that the outer portion is liquid based on the behavior of earthquake waves, and we'll learn more about that this semester. The mantle by far makes up the largest component of the Earth, 83%, and its main component is a mineral known as peridotite. The crust is just a thin outer skin of the Earth, and we can actually divide up that crust into continental crust and oceanic crust. Continental crust is thick. It's felsic. Felsic means that it contains more of the light, less dense minerals such as silicon and aluminum. The oceanic crust, on the other hand, is thin. It's young. It's dense. It's heavier. And it is composed of mafic minerals. Mafic minerals are dark, dense minerals and contain magnesium and iron. You'll learn more about felsic and mafic minerals when you get to the mineral section of the video lectures. Let's look at that division again of Earth based on the chemical differences. Notice we have an inner core which is solid, an outer core which is liquid. The mantle, obviously this diagram is not drawn to scale because the mantle is 83% of volume, and the crust would be so thin that we could hardly represent it on this diagram. We have both oceanic and continental crust, and if you look at that upper right inset, you will see the continental crust is much thicker and the oceanic crust is thinner. But wait a minute, they're also mentioning lithosphere in that inset. This is a physical division of the Earth. We can divide the Earth based on its physical characteristics as well, how earthquake waves respond to the different areas of the Earth. Based on physical characteristics, we're concerned with two divisions of Earth, and these are important in plate tectonics. The lithosphere is composed of the upper mantle and the crust. It is brittle. It breaks into plates, and this is the formation of the plates for plate tectonics. The asthenosphere is the layer immediately below the lithosphere. It surrounds the lower mantle, and it's plastic. Now, we don't mean plastic in the sense of plastic milk cartons. In the sciences, plastic means that it flows slowly. When a stress is applied, it does not break. It's not brittle. Instead, it'll flow very, very slowly. We also have other physical divisions of the Earth, including the mesosphere, but for our course, we're going to be concerned with the lithosphere and the asthenosphere. Again, this is just a different way to divide up our Earth. Note the continental crust and the oceanic crust, along with that upper mantle, compose the lithosphere. This is the brittle part of the Earth. The asthenosphere is the layer immediately below that, and it surrounds the lower mantle. How do we study the Earth? How do we begin to investigate the internal structure of the Earth? How does science progress? Well, let's take a little bit of time and review scientific methodology and how we know things and the level of knowing in science. We often refer to the scientific method, but you need to keep in mind that there isn't just one method and that scientists don't always do the same steps in the same order. The general method that we use to describe scientific methodology, though, is that we first observe what's going on around us. We see something, and perhaps we think we have a good explanation for it, a good testable explanation. We form a hypothesis. Then we design an experiment or experiments and collect a lot of data. With the data, we analyze the data and form a conclusion. The conclusion can either be an acceptance of our hypothesis, a rejection of our hypothesis, or perhaps we might have been on the right track, but we need further refinement of our hypothesis. Again, this is just one outline of a method of the progression of science. There are many, many different methods by which science progresses. More importantly, though, are the levels of knowing. As most of you are aware, there is a huge difference in meaning from the scientific community's use of theory and the average use of this word. A hypothesis is unproven, and it's an educated guess. Most people, the general public, use theory as if it were a hypothesis. In other words, if I get up in the morning and I say, I have a theory that it's going to rain today, that's not a theory, not in the scientific sense. My guess is that it'll rain today. My hypothesis, looking at the rain clouds gathering, that it probably will rain today, but it's not a theory. A theory in the scientific sense is the highest level of knowing. It not only is a good explanation to describe what's going on, but it is tested and retested and retested. It is predictive. We can use the theory to predict what will happen in the future. It is supported by a large body of evidence, and we cannot stress that enough. There is a multitude of data to support a theory. This is the best we have in science. If you want to insult a scientist, tell the scientist, oh, plate tectonics, that's just a theory. Theory is the highest level of knowing that we have, and our meaning of theory is much, much different from the average public definition of theory. We used to reference the law, and if you grew up about the same time I did, you learned that the law was the highest level of knowing. Not anymore. Law is old terminology. It's a formal statement and usually involves mathematics. A law describes what always occurs under very specific conditions. For example, Newton's universal law of universal gravitation does not apply as objects approach the speed of light, but it does tell us the force of gravitational attraction between two objects based on their masses and the distance between them. In the solar system, it works just fine, but as objects approach the speed of light, we have to defer to Einsteinian physics. A theory, on the other hand, isn't that specific. A specific set of conditions, a specific statement, is very narrow. A theory is more encompassing, it's supported by a large body of evidence, and it is predictive. As we study geology this semester, it's convenient to think of it as themes. We will categorize the processes and products we study into 3 themes of geology this semester. This is not an earth filing system. This is Renee Clary's filing system. We're going to look at plate tectonics, we're going to look at the rock cycle, and we're going to look at the age of the earth, all 4.6 billion years of it, and the processes that have modified it through time. And most of our discussions will directly relate to at least one of the 3 themes of geology. Plate tectonics, again, this is a theory in geology. This is a theory on line with the theory of organic evolution in biology. It's one of the most encompassing theories in the sciences. Plate tectonics holds that the lithosphere is divided into plates, and these plates move because of convection cells in the asthenosphere. We're going to spend a whole video lecture on plate tectonics, so this is just an overview. Note that the red lines denote where the plate boundaries are. And it's important to see, if you find North America there, right in the center of the slide, the upper center of that slide, you'll note that that North American plate not only includes the North American continent, but some oceanic crust as well. These plates move over the Earth's surface, over the asthenosphere, because of convection cells in the mantle. Now note that right below that crust you see those convection cells. The mechanism of how the convection cells work is still hotly debated in the geosciences, and we'll discuss that more when we get to plate tectonics. Why is plate tectonics so important? Why is this a unifying theory in geology? Well, most earthquakes and most volcanoes occur along plate tectonic boundaries. We also can find and locate mineral resources if we know something about tectonic plate boundaries. Tectonic boundaries also influence the distribution of life. There are 3 boundary types: divergent, convergent, and transform. And if we can have the camera on me for just a second, I'll briefly demonstrate what we're talking about. When we talk about a divergent plate boundary, what we're looking at are 2 plates that are pulling apart with tensional force. With a convergent plate boundary, we have 2 plates coming together. If we have 2 continental plates coming together, we're going to have collision and crustal thickening. If we have a continental and an oceanic plate coming together, we get subduction, where the oceanic plate is subducted underneath the continental plate. We still have a lot of force, a lot of compressional force. And the last plate boundary is that of a transform plate boundary. Imagine 2 plates moving past each other, parallel to each other, but in opposite directions. We have shear force in this case. Okay, back to the slides. The second theme of geology that we will encounter in this course is the rock cycle. What is a rock? In geology, a rock is defined as a solid aggregate of 1 or more minerals. Okay, wait a minute, we just introduced a new term. What's a mineral? Minerals have a very specific set of characteristics in geology. They have to be naturally occurring. So in other words, that lab-created diamond in New York City, although it mimics that mined diamond by De Beers in South Africa, it's not a mineral by our definition. Crystalline. By crystalline, we don't mean that it has to have a beautiful crystalline point like a quartz point. But crystalline means that the internal arrangement of the atoms and molecules occurs in a nice, regular order. A mineral is also solid. Those of you who grew up a long time ago in the Dark Ages, as I did, remember those thermometers that moms would have to shake down because there was the silver metal that would determine the temperature based on its rise in the little glass tube? Well, that metal is mercury. Mercury is the only metal which is liquid at normal atmospheric conditions, temperatures, and pressures. So by our definition of a mineral, mercury, even though it is an element, a metal on the periodic table, it does not qualify as a mineral. Minerals also have to be inorganic, which means that they cannot be produced by something that's living. Amber, which is fossilized tree sap, would not qualify as a mineral by this definition. And finally, minerals have a definite set of physical and chemical properties. Most rocks are composed of minerals, and we have three basic types of rocks. We will not only investigate minerals in another lecture, but we will also investigate each of these rock types during the semester as well. Igneous rocks crystallize from magma, or they can be consolidated from pyroclastics that are erupted from a volcano. Igneous rocks can be intrusive, forming inside the earth, or they can cool on the outside of the earth and be extrusive. The key to igneous rocks is that they start out from molten rock or magma. Sedimentary rocks are composed of fragments of rocks, pieces of pre-existing rock types, or they can also be precipitated from a mineral-laden solution. Metamorphic rocks are the last of our rock types, and a metamorphic rock occurs when we have an existing rock that is altered in the solid state, and it can be altered by heat, pressure, or by chemically active fluids. Now the key here is solid state. What happens if we have a sedimentary rock, for example, a sandstone, and we add heat and pressure to that sandstone and change it into a quartzite? We have a metamorphic rock. We have changed an existing rock into a new rock, so we now have a metamorphic rock type. What if we keep adding heat and pressure to that quartzite and melt it? We no longer have a metamorphic rock, but we have an igneous rock when it cools. Once we have molten material, we start over with the igneous process. Here are some photographs of igneous rocks. That in your upper left-hand corner is granite. It is an intrusive igneous rock. In the lower right corner is basalt. This is the most common extrusive igneous rock. Think Hawaii. Here are some pictures of sedimentary rocks. The one in the middle toward the top is a sandstone. The larger particles, the left bottom, is known as a breccia. These are angular particles that have been compacted and cemented together. And over to the right is a core of rock salt. This salt was precipitated as the water evaporated and left behind the minerals that were dissolved in the solution. And finally, here are some examples of metamorphic rocks. There is a piece of marble, a chunk of marble in the upper left corner, and in the lower right corner, this is known as gneiss, G-N-E-I-S-S, and it forms the basis of all geological jokes that start with "have a nice," G-N-E-I-S-S, day. Geologists are constantly looking for humor. How are all of these related? Here is a diagram known as the rock cycle, and you will note that there are different rock types that are depicted in this diagram, and we also have lots of processes. But just as we noted with the spheres and the interacting systems or subsystems of our megasystem Earth, we don't have a nice circular path that's always followed in the rock cycle. For example, let's start with transportation in the upper left corner. We have different sediments that are transported, they are deposited, They're compacted and cemented together. That's known as lithification, and we get a sedimentary rock. Well, if heat and pressure are added to that sedimentary rock, we can get a metamorphic rock. But note, we don't have to metamorphose that sedimentary rock. What if that sedimentary rock is exposed at the surface again? Well, it can be weathered, and guess what? We end up with more sediments, more particles that are then transported, deposited, cemented, and compacted to form a new sedimentary rock. Note on the right side of the diagram we have igneous rocks. We have a body of magma at the bottom, and if that magma rises and cools inside the earth, we have an intrusive igneous rock. However, the magma can rise to the surface. At that point we call it lava. And when that lava cools on the surface of the earth, we have an extrusive igneous rock. The thing to keep in mind here is that there are multiple pathways. One rock type does not always lead into another rock type, and that we can take shortcuts all throughout this diagram, and not all of them are represented here. The earth is complicated and doesn't follow a nice little recipe. There are different rock cycle animations available on the web, and hopefully if you access this one, you will see one created by the Geological Society of London. I'm a little hesitant to use web links because they are notorious for changing on me. I usually check them the day before I put them out, and even then I've had some problems where it stopped working within 24 hours. If this one doesn't work, go ahead and do an internet search under rock cycle animation, and you should be able to find some that better depict some of the processes, not all of them, but some of the processes involved in the rock cycle. Now remember, this is what I call another theme in our study of physical geology this semester, but it's not in isolation, and as you might suspect, the rock cycle is closely intertwined with plate tectonics. If you look, for example, in the left-hand part of this diagram, you see upwelling toward the bottom. That is meant to be a divergent plate boundary at the mid-oceanic ridge. As that magma comes up and breaks through the surface, we're going to get an extrusive igneous rock. Note what happens to that plate on the right side of that mid-oceanic ridge. It is being subducted over an overriding plate. Note that that plate moves down below what is a chain of volcanoes. It gets to a certain depth. The plate is dewatered, melting occurs, that magma rises because it's less dense than the country rock, and if it erupts on the surface, we get, again, an extrusive igneous rock. With all of that pressure associated with subduction, as you might imagine, we get a lot of metamorphic rocks associated with subduction zones and trenches. Note too, look at the volcanoes. They're exposed at the Earth's surface, and therefore they're subjected to ice, water, rain, wind, so they can be weathered and eroded. The sediments are transported down, probably by rivers, to the edge of that continental plate there, and they are deposited. These sediments are deposited, and as more and more sediments are deposited on top, the compaction and cementation take place, lithification take place, and we create sedimentary rocks. So the point here is that the rock cycle is very closely intertwined with plate tectonics. And last but not least, my third theme of geology is going to be geologic time, and one of the big words in geology, uniformitarianism. The geologic timescale summarizes Earth's chronology, all 4.6 billion years of it. It's a man-made filing system, but it's based on radiometric dating, or decay rates of certain elements that are radioactive, and we'll learn more about this later in the semester. We can also use what are known as relative age dating methods. We know which layers occur first because of their placement, and again, we'll study this during the semester. How do we look at rocks that are exposed and reconstruct what happened in the past? We do this by the principle of uniformitarianism. And what this means succinctly is that the present is the key to the past. We look at the processes occurring on Earth's surface right now, such as rivers, wind, glacial processes, and we see the products that result from these processes. Then, when we look back in the rock record that may be exposed at a cross-section or a road cut, we then hypothesize what happened in the past based on the products. If we see the same sorts of deposits in the rock record that we see being created today in a delta region, we hypothesize and know that this was deposited by an ancient river system in a delta environment. It's important to keep in mind that rates may have varied in the past. There may be some events that have been catastrophic in Earth's history. Most of us have heard about the meteorite impact, which may have hastened the demise of the dinosaurs. And fortunately, we don't have meteorite impacts occurring every decade. So some of the rates may have varied in the past. But in general, we use the processes we observe today and hypothesize that these occurred in the past at pretty much the same rate that they do now. And finally, here is a diagram depicting the geologic time scale. It is not to scale. If you note toward the bottom, we call this the Precambrian. That's an informal term. But the biggest unit that we use in geology for time is the eon. And the Precambrian consists of 2 or 3 eons, depending on which author you're citing. But the Phanerozoic eon is our current eon. It's 542 million years to today. We're still in the Phanerozoic eon. Everything below 542 million years ago is referred to as the Precambrian, and as you can see, that constitutes most of Earth's time. We're only looking at the last 500 million years in the Phanerozoic eon. Because so much happens within an eon, we find it convenient to divide eons up into eras. And in the Phanerozoic eon, we divide up into the Paleozoic, the Mesozoic, and the Cenozoic eras. We can divide eras up into periods. Look at the Mesozoic, and you see that the periods are Triassic, Jurassic, and Cretaceous. Where have we heard Jurassic before? Now we know where Steven Spielberg got the idea for his movie. And finally, we can divide up periods into epochs. Epochs are smaller divisions. We can even go a step further and divide epochs into ages. You note that this diagram is a little top-heavy, and the reason for that is as we get closer to the present time, we have more and more evidence in the rock record which is available for us to determine what happened. So it's more convenient for us to divide up time into smaller and smaller units so that we can communicate a little bit more effectively with other scientists who are also studying the same thing. Okay, that marks the end of our first video lecture in Geology 1, Processes and Products. Thank you so much for joining me today. If you have any questions, if you need further clarification, please feel free to post a question on the discussion board or contact your instructor. I look forward to seeing you next time. Thanks, and have a great day.